viewers, and welcome to another episode of Space Science with Python. Last time we generated our first statistics and data scientific insights of the Comet database we generated a week ago, and we had a special focus on the P and the C-type comets. So just a small recap, the P-type comets are the comets with a period of less than 200 years, and the C-type comets are the long period comets, so one revolution around the Sun takes them more than 200 years. And what we did, we extracted the inclination and the aphelion data or orbital elements of each comet and generated the scatter plot. So small recap also, the aphelion is the point farthest away from the Sun that the object can reach. We saw that the eccentricity of the C-type comets is very large, so it's a very elliptical orbits, and we focus only on closed orbits, so comets with an eccentricity smaller than 1. So these comets will eventually come back into the inner part of the solar system. So what we saw on the x-axis, on the y-axis was that first of all we had to make a logarithmic plot because the distribution of the aphelion values of the C-type comets was largely scattered between, let's say, 10 AU and 10,000 AU. And the inclination also varied from 0 to 180 degrees. We saw that for the short period comets, we see, I would say, yeah, with the naked eye you can see maybe here two distributions basically, yeah, in the aphelion distribution. And the P-type comets are, yeah, they are scattered, not really largely scattered, they are focused, let's say, closely at the ecliptic plane. So there's no large variation. Of course, it's not like our planets in the solar system where every planet is more or less moving on the same plane. Here it's a little bit more scattered, up to 40 degrees or 20 degrees. But for the C-type comets, we see basically some random scattering along the aphelion values and also along the inclination. So the question today is, what is this C-type comet all about? So today we will focus on the C-type comets to get a better understanding and idea what this is all about. And we will focus especially on the inclination today. So we will derive a distribution of the inclination. And yeah, for the aphelion, we simply see, well, the values vary between, let's say, 10 and 10,000 AU. So let's take a look at the inclination. And for this, I created, again, a small script for you today. And it's also, again, some kind of plotting we will do today to see the difference between the P and the C-type comets to interpret especially the long period comets. The name of the video is a little bit a spoiler already. It's called the Oort Cloud. Maybe some of you have heard about it, but we will get to this a little bit later. So what do we want to do? We would like to create a distribution of the inclination of the P and C-type comets. And of course, what could one do? Yeah, let's generate a histogram plot. But don't worry, we will not exclusively focus on a histogram. This is maybe a little bit boring and trivial for you. We will later also cover something that's called kernel density estimation. So the kernel density estimation is something that's really helpful to generate, let's say, a visual, to create a proper visual representation of discrete data points. But let me first code a little bit here. Like last time, I'm setting a dark background, increasing the font size to make it a little bit more fancier, and again creating a figure and axis with the subplots command. Where is it? There. And a similar figure size as last time, 12,8. And we can now create a histogram with the inclination. So what we can do, we want to plot P-type and C-types, and we could simply use the multi-cursor again, but then we have to be aware that we are copying the same text, or we will just simply copy paste it later. I think in this case, a multi-cursor is a little bit of an overkill, so let's do it step by step. So we want to draw the inclination in degrees. And the point is that maybe it's not auto-completing because I didn't run it yet. Yeah, maybe then I get a little bit better auto-completion suggestions for the columns. Let's now take a look at the data. Today we'll also learn a little bit about bin sizing and so on. So maybe we'll do it later here. Let's create a density plot. So to scale it between P and C type, let's create a color. Again, you know me, orange is my favorite color. I choose first. Maybe a little bit fancier, some transparency, and setting a label. The label is again the P type. Okay, so let's copy paste the histogram. We have it for P type. Now we have it for C type. We do it for, choose blue. Actually, it makes also a little bit sense. I mean, yeah, not sense, but the P-type comets have a shorter period. They visit the sun more frequently, so they're a little bit, let's say, hotter. So orange is suitable. C-types are, moving to the outer space, so they are colder, which is blue. Of course, this is not scientifically correct. It's just, maybe it makes a little bit on a meta level. It makes a little bit sense what I'm saying. The inclination, again, is limited between 0 and 180 degrees. So let's set a limit between 0 and 180 degrees. And we can also already set an X label and a Y label so that we have a proper text there. Inclination in degrees. Also very important in all these plots, always write down the dimensionality. So simply writing inclination is not very helpful. Actually, one should also write inclination given in ecliptic coordinates in degrees. But here, okay, we're in the solar system. In the paper, you can write this maybe as a subtext or so. But always write the physical dimension. In this case, it's degrees. If you use temperature, is it Kelvin? Is it degrees Celsius? Distances, meter, kilometer. That's very helpful. For you, it's maybe trivial and easy to understand, but for another person, the person would say, no idea what you're talking about. So also here, we have also here our color, orange and blue. We have we picked some transparency, so it's not too bright and will not burn our eyes. And you may remember that in the legend, it will be helpful to set the alpha value of the color to 1. So let's create also here in our case a legend first. So this is like a copy of what we did last time. Fancy box equals 2. It's not a shame to use maybe the same logic for the other plots. I mean, if you read also a paper or something, then it's useful to maybe also follow a common styling guideline, because then it's also easier for the reader, because then he or she is familiar with your style in the paper and follows you a little bit easier. So there's no shame, let's say, to stick with a certain style. I mean, it's not the style we will have all the time, but in this case, it's okay. So what I do here is I iterate through the legend handles of the legend. And now I set the alpha value for each individual legend to 1, so that the legend is a little bit, has no transparency. So let's have a look at the distribution. And this is what we see. So we see the P type, the C type, the normalized distribution. So here you see from 0 to 180 degrees. And here the P type in some certain bins. Now you already see a distribution, right? You could now start your analysis, but this video today is also a little bit about this visualization of discrete data. So of course, most of you know maybe histogram, right? So you choose a histogram, you use it, you choose Python for it, matplotlib, whatsoever. You plot it, you're fine, everything is cool. But who tells me that for blue, so for the C-type, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins are the perfect solution? Why 10? Why not 5? So why can't I choose bins bins equals 5? Yeah, I use it for maybe for the histogram here and also for the histogram here. Yeah, it's also valid. And now for the p-type, I don't see any nice distribution, only basically everything is between 0 and 30 degrees. Yeah, what's the correct bin number? And some of you may know or not that there are certain rule of thumbs for the bin sizes. Maybe let's start with something, yeah, the most, I would say, commonly used definition of how to, or function of how to determine the number of bins. We can create a lambda function for this. So the number of bins, yeah, is equal to a lambda function where we will put there a data array, so data points. And there are a lot of different definitions. One definition I would like to show you is based on the square root of the length of the data array. So 100 data points. So we have 100 data points between 0 and 180 degrees leads to square root. Yeah, it's 10. So the number is 10. 10 bins for this distribution. If we have 105 or so, then it's not really an integer. So we have to round the values. We round it down. So we need the floor function of this. And well, I think later it's an integer is required. So let's be sure and write down the integer. So this is our function now. And that way we can now use our small function to compute the number of bins in this part here. We can even maybe print first the number of bins for each. I should maybe write number of bins, not bin. For the p-type, yeah, I should take care. It would be 25, yeah. And for the C-type, it would be 15. So different number of bins. So this is what we can use now. But I will tell you also in a second that this is also not the perfect solution. Now, come on, mouse, cooperate. Okay, so I think I copied this C-type, right? So let's put it here. Yeah, C-type, and P-type is here. Replace it with the P. Replot it, and we have a little bit clearer distribution now. We see even that here, the peak of the normalized distribution for P-type is not at 0 and 10 degrees, it's somewhere else. Of course, we need also now to extract the bin range and so on to really get the actual ranges, but let's stick with this one here first. And we see that the C-type is, yeah, I would say almost uniformly distributed, but this needs also to be tested, right, statistically. The question is now, is this now the best case to visualize the data? Now, there are different concepts because the classical histogram does not consider the information density. So for example, here in this area where we have a lot of data points, the information density is way higher than the points that are here. It's way more scattered. We see only a few bars, a few bins, if at all. And there are different concepts. One concept is, for example, so-called the Bayesian blocks. I will put a link into the description so that you know what this Bayesian blocks are all about. It's like a histogram where the width of the bins are being adapted, or they have an adaptive width depending on the information density. So where you have sparse density, information density, like here between 60 and 180 degrees for P, it will probably just create one large bin. And here in the denser regions, it will create smaller bins, so that you see a way more differentiated view of the distribution. Another point is the so-called kernel density estimator, or estimation estimator, the KDE I would like to show you today. What does it do? The histogram is like summarizes the number of points per interval. So in this interval here, let's say between 0 and 10, we have a few data points. Between 10 and 20, we have a few data points, and so on. And the kernel density estimator replaces each dot that is virtually, let's see, somewhere here. It replaces the dots with a function, for example, with a Gaussian function. So the dot is replaced by a Gaussian function, and then we have a lot of Gaussian functions. We summarize the Gaussian functions, so we have a like a superposition of all these functions, and we get a smooth distribution of, let's say, in quotation marks, the actual distribution. Here, there are also different ways to compute this. We can use the Gaussian kernel, the Gaussian function. Also, it can be applied in 2 dimensions and so on. But there are also other functions, like, for example, the Epanechnikov kernel. We will get to this in a future video when we are talking more about structures and data. But for now, let's stick with the Gaussian kernel. And also here, the width of the Gaussian kernel can either be set to a scalar, to a single number that applies to all Gaussians, or there are also methods where you can adapt or have an adaptive Gaussian width for each Gaussian depending on the density of neighboring points. So a higher density leads to a smaller Gaussian width. And then you see finer structures, and in areas with less data points, like here on the right side for our p-type comets, the Gaussian width becomes broader and it gets more smoothed out. Now the adaptive things is something for the future. For now, we start with the very simple approach. Now here we have a histogram based on a certain rule, and now we can use the Gaussian kernel from another package called SciPy. There's also other package, scikit-learn, but this will also be covered. Let's use SciPy for now. And SciPy, very important, it has been added to the requirements txt. So if you want to import it, maybe I should have said this earlier, you need to rebuild your remote container on VS Code, or you install it in the command shell via an ! pip install and then SciPy. Yeah, but here in my case, I already installed it. Now, for SciPy, we need to import it from SciPy import stats. Yeah, this is like the statistics part module. We need to define an inclination range for our kernel. So linspace, it is like between 0 and 180 degrees. Let's take it in 1000 equal steps. And now we can create a kernel for the p-type comet. So p-type, let's call it inclination kernel, equals to stats.Gaussian stats.Gaussian KDE. And there we have then the p-type of the inclination of the p-type comet. Yeah, this defines the kernel. And now for the distribution, to compute the distribution, we use now the kernel p-type inc distribution. So the distribution is computed by using the kernel we defined here. And we apply the inclination range array we defined here in command line 3. Now let's copy paste it and change the letters for the C type. And let's see. Yeah, no error. Perfect. So it was quite fast, or a fraction of a second. And now we can add this kernel density estimator to our plot. Let's stay also with the histogram so that we see a little bit the difference. it's also important to know that the distribution we get is a normalized distribution. So if you want to get, let's say, scale it with the numbers, you have to, of course, multiply the original length of the data array. So, but here we have everything is normalized. So let's say inclination range and the p-type inclination distribution. We take the same color, tab, orange, and the alpha value is 1. Line style, let's say line style equals solid. And then the same thing also for C-type, because as I told you last time, you should also have different colors. Now for histograms, maybe you can use some kind of background pattern or something to distinguish it, because if somebody prints it now out on a black and white printer, it's quite difficult to distinguish between those two. So we can maybe distinguish it by using a different line style for P and C types. So let's use it here for dashed, and then it's a little bit easier to understand. I executed this command. Yeah, perfect. So this is now the distribution, as you can see. Yeah, so it fits quite well with the histogram, of course. So we see here distribution. Yeah, you can now use this distribution to compute the median, also the width, and so on, the skewness and whatsoever. And for the C-type, we see that it's, I wouldn't say it's uniformly distributed, but almost, right? I mean, the theory of uniform distribution can now be tested, but yeah, let's assume it's now uniformly distributed. And what does it now mean for C-type? It means that the comets, they come, or their inclination is quite, let's say, and completely random. So their origin, where they come from, is isotropically distributed. So there is no region of preference where these comets are, or where they come from, and what kind of orbit they are. On the other hand, the P-type comet, they are quite concentrated along the ecliptic plane. So here we have a strong preferred region of the comets. But for the C-type comets, it's not the case. They are basically everywhere, let's say it this way. Now we have hundreds of comets, but over 100 years ago, we only knew a few. Only a few comets were known, only a few orbital elements were known. And based on these few observations, Jan Oort and Ernst Öpik, so astronomers from the last century, they had a hypothesis. They said, well, if the C-type comets, the long period comets, they are so isotropic, and the aphelion, just recall it here, they range up to 10,000 or 1,000, 10,000, maybe 100,000 AU, and the inclination is more or less uniformly distributed, there has to be a source around our solar system, formed like a sphere, where these comets come from. And this hypothetical sphere of a comet source is called the Oort Cloud, the name of today's tutorial session. So let's have a look at the Oort Cloud on Wikipedia. It's a quite nice visualization. This is like the hypothesis, how it may look like. We have here in the inner part, on the upper plot, the inner part of the solar system, we have here our planets, we have here different orbits. Here, for example, this is Pluto's orbit, a little bit more inclined than the others, so all the other planets are more or less on the ecliptic plane. Then in the outer region, after Neptune or so, we have something called the Kuiper belt, which is also concentrated along the ecliptic plane. You can see it a little bit here, it's quite a little bit concentrated. But then far away, more outside, at 100,000, 10,000, 100,000 AU, we have a huge distribution, isotropic distribution, so there's no preferred region or direction of comets around our solar system, which is called now the Oort Cloud. And you see here that it could be that there are billions of them. So for now, we only know a few hundred, but there could be billions. We don't know the exact number. It's quite difficult to observe, let's say, 1 kilometer sized comet that shows no activity at a distance of, I don't know, 10,000 AU. So this is, of course, a hypothesis that is somehow supported by our observations of the C-type comets, because they come, or their inclination is pretty random. Yeah, there's no preference of prograde orbits to retrograde orbits. It's basically the same. So there's no preferred inclination distribution like for the P-type comets, and also the aphelion values, they range to, I don't know, 10,000 AU and more. So this is the hypothesis just simply based on these two orbital elements and the distributions. So with simple plots, with simple data science, I mean, we didn't use any sophisticated analytics methods, just simply plotting it and using some KDE, we found out that this hypothesis is currently the best well-suited theory for the origin of the C-type comets, of the long period comets. So how does it happen that sometimes comets come into the solar system? Well, of course, their orbital period is very large, thousands of years, and some are not coming close to the sun. They are maybe orbiting in this cloud. Then you have a neighboring star passing by, causing gravitational perturbations, and then they change their orbital elements slightly, but in such a way that their orbit becomes highly elliptical, and then they fall into the inner part of the solar system and then escape again. Yeah, maybe they get even some momentum, and they have an eccentricity larger than 1, so they even escape the Oort cloud and fly into the interstellar space. So as a small recap, this is what we basically did. Yeah, we used the simple distribution here and the scatter plot here to identify or also see that where the hypothesis of the Oort cloud comes from. So this is what we did. So the C-type is, let's say, yeah, we understood it more or less. Yeah, I mean, of course, there's more theory behind the Oort cloud from a dynamical perspective and numerical perspective, how it evolved and so on. But simply with the data we downloaded, we understand what we see here. For the P-type comets, well, there we need a little bit more analysis. We will also introduce, or I will introduce next time, a new astrodynamical property, which is called the Tisserand parameter. And you will see what kind of relationships these comets have with the largest planet in the solar system, namely Jupiter. But until then, take care and see you next time.